Hello, everyone. Welcome to a new lecture of our course on processing in memory. And today we have again Geraldo Francisco de Oliveira presenting another interesting proposal about using processing in memory to accelerate and make more energy efficient an important application. In this case, or today, he's going to talk about hybrid transactional and analytical databases. Geraldo, when you're ready, feel free to start.
Thank you so much, Juan. So today I'm going to continue talking about how to do hardware software co-design to accelerate data-intensive applications. Last week we saw a case with machine learning, particularly neural network inference for edge computing. And today we are going to talk to the other spectrum of that of the computing environments. We are going to the cloud, and then we are going to talk about hybrid, how to use process memory to accelerate hybrid transactional and analytical databases. So before I start, so this work was led by Oliveira, who is now at Google. So before we start, I'm going to give a briefly summary of what this talk is about. So many applications today need to perform real-time data analysis using what we call a hybrid transactional and analytical processing system, or HTAP. And an ideal HTAP system should have at least three key properties. So should provide at least three properties, which are should provide high data freshness and data consistency, workload-specific optimization, and performance isolation. We extensively evaluate state-of-the-art HTAP systems, and we see that they fail to provide all of those three HTAP properties at the same time. Therefore, our key idea to solve this issue is to divide the HTAP system into two isolated process islands, one for transactional workloads and another one for analytical workloads. Each island is occupied with a set of optimized hardware resources and algorithms. So by enabling processing islands, we can perform workload-specific optimizations to transactional and analytical workloads while providing performance isolation. So we leverage our key idea to design Polynesia, which is a novel hardware software cooperative design for in-memory HTAP databases. So we implement custom algorithms and hardware in Polynesia to reduce the cost of maintaining data freshness and data consistency in HTAP systems. And we exploit processing memory for the design of the analytical processing islands to alleviate the cost of data movement. We extensively evaluate Polynesia against three state-of-the-art HTAP systems, and we observe that it increases transactional analytical throughput by 1.7 times and 3.7 times on average, and also reduces energy consumption by 48% on average. So here's the outline for this talk. So first, I'm going to give a brief introduction about HTAP systems. Then I'm going to talk about the limitations of current HTAP systems, which is going to motivate, Polynesia. Then I'm going to give Polynesia a high-level overview of Polynesia, and then talk in details about Polynesia's update propagation mechanisms, consistent mechanisms, and also the analytical engine. Then I'm going to give a brief summary of our evaluation results and finally conclude. So let's get started with the introduction of HTAP systems. So recently, in many different application domains, there has been an explosive interest in performing analytics on the most recent version of the data, doing real time. So here we have an example of self-driving cars, which is one example of such application that require computing data while the data is being produced. So self-driving cars ingest a large volume of data from various sensors during the run of the car. And typically there is some form of learning model running the car itself or in the cloud that needs to apply decisions based on the real-time data that has been collected. Other applications that require real-time data analysis includes fraud detection, personalized recommendations, and also healthcare monitoring. Therefore, for these applications, it's critical to perform data analytics in the most recent version of the data, since the value of the data diminishes over time. So traditionally, database management systems use two separate systems to perform transactions and analytical over some data. This creates an issue since data migration between transactional and analytical database database management systems can take from hours to days, depending on the volume of data. To solve this issue and support real-time data analysis, Parallelworks have proposed the design of a hybrid transactional analytical system. As the name indicates, such a system has the ability to perform both transactional and analytics concurrently. So in order to allow for real-time data analysis, our HTAP system should provide three properties. So the first one is that HTAP system needs to provide workload-specific optimizations, meaning that both transactional and analytical workloads must benefit from their own specific optimizations. The second one is that the HTAP system needs to guarantee that analytical workload access the most up-to-date version of the data while ensuring the consistent view of the data in the entire system. And the third one is that the latency and throughput of transactional and analytical workloads should be as if they are running in isolation. However, as I'm going to show next, it is really challenging to achieve all of those three HTAP properties concurrently for a given HTAP system. So next, I'm going to talk more about the limitations of state-of-the-art HTAP systems. So we studied two major types of HTAP systems. So the first one is called a single instance design, where both analytics and transactional workloads run on a single copy of the data. And then we also have the multiple instance design, where each workload which workload runs on different copies of the data. So transactional workloads run on some copy of the data, while analytical workloads running a different copy of the data. So we find that neither type can achieve all of the three desired HTAP properties. Specifically, we observed that the two tricky problems for both designs. The first one is that data freshening inconsistent mechanisms on state-of-the-art HTAP systems are costly to implement and cause a drastic reduction in both transactional and analytical throughput. And the second one is that HTAP system fails to provide performance isolation because of the higher contention at the main memory. Next, I'm going to show the limitations of state-of-the-art systems in more details. We start with the single instance design. So one of the major problems with the single instance design is the high cost of maintaining data consistency. So there are two main mechanisms to maintain data consistency in a single instance HTAP system. The first consistent mechanism is called snapshotting. During snapshotting, when a transactional update happens, the HTAP system creates a copy of the transactional data and send it to the analytical replica. Snapshotting happens every time a transactional workload updates a row or a tuple in a column in the main replica. The second consistent mechanism is called multi-versioning concurrency control, or MVCC. In MVCC, instead of replacing the old data in a tuple when updates happen, as it's in the snapshotting approach, the system creates a new time-stamped version of the data that is chained together with the old version of the data, forming a pointer-based version change. During the execution, instead of reading a separate snapshot, analytical query can simply use a timestamp to read the most up-to-date version of the data at the time the query starts. We evaluate the impact of snapshotting and MVCC on transactional and analytical workloads. So this plot here shows the impact of snapshotting on the throughput of transactional workloads for a very number of analytical queries. We compare the snapshotting-based system against a hypothetical system where snapshotting has zero cost. We observe that transactional throughput reduces by up to 75% when increasing the number of analytical queries. The main source of throughput loss comes from the cost of executing the memory copying operation required during the snapshotting execution, which generates a large amount of data movement. Next, we evaluate the impact of MVCC on the analytical throughput for very numbers of transactions. We normalize the analytical throughput to the system where executing MVCC has zero cost. We observe that the analytical throughput loss of up to 42% when employing MVCC, and such throughput loss comes from the fact that MVCC requires traversing long version data chains when MVCC needs to execute, which leads to expensive timestamp comparison operations and also a large number of random memory access, which can be extremely costly. Next, we study the drawbacks of a multiple instance HTAP system. So a major challenge faced by multiple instance HTAP systems is how to keep analytical replica up to date. In order to maintain data freshness, multiple instance HTAP systems perform an operation called update propagation, which is divided into two steps. In the first step, the system needs to perform the update, gather, and shipping operation, which collect updates from transactional threads and send them to the analytical replica. Second, the system needs to perform the necessary format conversions between transactional and analytical data. So we evaluate the cost of update propagation in a multiple instance system. So here in this plot, we evaluate the transactional throughput from varying numbers of transactions and also update read ratios. We compare the transactional throughput of a system where the update propagation has zero cost with a system that performs only update gathering and shipping and a system that performs the entire update propagation process. We observe that from the figure that the transactional throughput reduces by up to 21.2% during the update gathering and ship process, and further reduces to 42.2% during the update application process. We conclude our analysis by identifying three major limitations of state-of-the-art HTAP systems. First, they do not meet all of the desired HTAP properties, failing to provide high data freshness and data consistency, performance isolation, and workload-specific optimizations at the same time. Second, data freshness and data consistent mechanisms suffer from data movement overhead and are highly data intensive, leading to a reduction in transactional and analytical throughput. Third, the system fails to provide performance isolation due to the high contention in main memory. Based on that, our goal in this work is to take advantage of custom algorithms and hardware to address such limitations of current state-of-the-art HTAP systems. Next, I'm going to give an overview of our proposal, which is called Polynesia. The key idea behind our mechanism is to partition the computing resources in two types of isolated and tailored processing islands, where each island is dedicated to either transactional or analytical workloads. By isolating transactional workloads using transactional islands from analytical workloads using analytical islands, we can apply workload-specific optimization to each island, avoid high memory contention, and also we can design efficient data freshness and data consistency mechanisms while maintaining data movement overhead at low cost. So Polynesia leverages processing memory techniques to reduce the data movement caused by data freshness and data consistent mechanisms. Processing memory can mitigate such overheads by adding computing units near or inside the memory device. In this case, we are going to use a 3D stack memory device. So based on the concept of process islands, we propose Polynesia, a hardware software co-designed HTAP system. Polynesia includes tailored transaction and analytical islands that include a replica of the data, optimized execution engines, and a set of specialized hardware resources. Next, I'm going to briefly describe the main components of Polynesia. So first, we have the transactional islands, which includes an execution engine tailored for transactions and a replica of the data. The transactional islands is designed to sustain high transaction update rates, that it uses conventional multi-core CPU systems with a deep cache hierarchy, since transactional workloads benefit from such CPU organization. Second, the analytical islands is implemented inside the logic layer of a 3D stack memory, as depicted here in the picture. So the 3D stack memory connects layers of DRAM banks with a layer of logic using high throughput through silicon vias or TSVs. The vertical partitions of a 3D stack memory is called a vault, and we place hardware resources inside each vault of the 3D stack memory, including an execution engine tailored for analytics and a replica of the data. The analytical island is designed to provide high read throughput. Thus, the analytical island leverages simpler processing memory cores that can mitigate the data movement caused during the analytical processing. We co-design algorithms and hardware units that can efficiently maintain data consistency and data freshness in your analytical islands. Next, I'm going to describe the design of our consistency and data freshness mechanisms in details. So we are going to start with the update propagation mechanism. So recall that to maintain data freshness, the HTAP system is to first gather updates from the transactional thread and ship those updates to the analytical thread and apply those updates to the analytical replica, thus applying the necessary format conversions between transactional data and analytical data. So first, we start with our update gathering and shipping process. Our update gathering shipping algorithm has three major steps. First, for each thread in the transactional engine, Polynesia stores the other update log for the queries performed by the transactional thread. The first stage is to scan the per-thread update logs and merge them into a single final log, where all the updates are sorted by their commit ID. The second stage is to find the location of the corresponding column in the analytical replica associated with each update log entry. You observe that this stage is one of the major bottlenecks of the update shipping because the fields on each tuple in the transactional islands are distributed across different columns in the analytical islands. Since the column size is typically very large, finding the location for each updating is very time-consuming. To overcome this, we maintain a hash index of the data on the column row key, and we use that to find the corresponding column for each update in the final log. The final stage is to ship these updates for each column to the analytical replica. We observe that the second and third step of our algorithm generates a large amount of data movement and accounts for 87% of the total algorithm's execution time. In order to accelerate our update gathering shipping algorithm, we designed a new hardware accelerator called the update gathering shipping unit. Our accelerator has three main building blocks. So the first, we have the merge unit, which is responsible to scan the update logs from the transactional thread and merge them into a single final update. To do so, the merge unit uses a three-level comparator tree. Second, it has a hash lookup unit, which is responsible to find the column location in the analytical replica for a particular transaction update in the final log. To do so, the hash lookup decouples hash computation from a hash bucket traversaling using a front-end FSM engine, probe unit, and a reorder buffer. This allows to issue concurrently hash lookups, thus maximizing the memory bandwidth utilization. Third, it has a cop unit, which uses read and write comments to fetch the hash bucket from a memory and also to send transactional updates to the analytical replica. The cop unit has multiple fetch and write back units, which allows to issue multiple memory access concurrently. Next, we describe the overall idea behind the update application process that we implement. Its main goal is to perform format conversions and apply updates to the analytical replica. Transactional analytical workloads benefit from different data layouts due to the respective computation patterns. In your relational database, the transactional workloads store data using a row-wide format, where each row represents an entry in the database and each column represents different features in the database. On the other hand, the analytical workloads store data in a compressed column-wide format, where each column stores several entries for a given feature in the database. In order to apply the transaction updates to the analytical replica, the system needs to first convert the data from the row-wide format to the column-wide format, and also reconstruct and recompress the column dictionary used for the compression of the analytical replica. Next, we describe our update application algorithm, which is designed taking into account the process memory characteristics and constraints. Our algorithm initially builds a sorted dictionary for only the update. Once the dictionary is constructed, we now have two sorted dictionaries, the old dictionary and the updated dictionary. Then we merge those two dictionaries into a single dictionary using a linear scan operation. We maintain a hash index that links the old encoded values in the column to the new encoded values. This avoids the need to decompress the column and add updates, eliminating the data movement and random access while reducing the number of dictionary lookups required. Finally, we construct the new compressed column by using a hash index and the new dictionary to find the new encoded values for each entry in the column. We designed a hardware implementation of our algorithm called the update application unit and added to each in-memory analytical island. The unit consists of three main building blocks. First, we have a sort unit that uses a 124 value bitonic sorter, whose basic building block is a network of comparators. These comparators are used to form a bitonic sequence where the first half of the sequence is monolithically increasing and the second half is monolithically decreasing. Second, we use a hash lookup unit to parallelize the column compression properties. So this hash unit has a similar design as the hash lookup unit in our update gathering shipping unit. And finally, we have a merge unit to merge the old update values in the old dictionary to the new update values in the new dictionary. Our measure unit also have a similar design as that one in our update gather and shipping unit. Oh, sorry. Next, I'm going to describe our consistency mechanism. So our consistency mechanism relies on a combination of snapshotting and versioning to provide data consistency for analytical queries. For each column in the analytical replica, there is a chain of snapshot where each chain entry corresponds to a version of a column. Differently from snapshotting, Polynesia does not create a snapshot every time a column is updated. Instead, Polynesia first marks the column as dirty, and then Polynesia creates a snapshot for a column if there are any dirty columns and no current snapshot exists for a particular column. In this way, Polynesia avoids long version chains as in the MVCC approach. To accelerate our algorithm, we employ a hardware accelerator that can do fast memory copying operations, which is similar to the copy unit we designed for the update propagation unit. The copy unit has a multiple fetch and write back units to issue concurrent memory access to main memory, a tracking buffer to track outstanding reads from DRAM, and also triggering writes as soon as reads arrive back from DRAM, and a hash index used to accelerate the read lookups into the trash that needs to go into the tracking buffer. Finally, I'm going to describe our analytical engine. So efficiently executing analytical queries depends on three main design decisions. So the first one is how to do data layout and data placement of the analytical data, how to do task scheduling of analytical threads, and how to map the physical operators as a scan and merge into these analytical execution engines. As prior works have shown, the execution of physical operators of the analytical queries can be accelerated by using process memory techniques. However, process memory performance is going to be suboptimal without proper data placement and task scheduling that avoids process memory constraints. Thus, we design novel data placement and task scheduling policies for our analytical engine. So I'm going to describe our data placement strategy next. The main problem related to data placement is how to partition analytical data across the varying number of vaults in the 3D stack memory, since that is going to impact the bandwidth available for the analytical replica and also the area and power available for the pin cores for the particular analytical engine. So let's assume, for example, that we want to partition 4 different analytical columns into 4 vaults in our 2D stack memory. So there are three main approaches to do so. So the first approach is to locally partition each column to each vault, to partition each column to a single vault. Thus, a column is going to be entirely contained in a single vault. However, since each vault has a fixed area and power budget and contributes to a fraction of the total memory bandwidth of the 3D stack memory, this approach limits the area, power, and bandwidth available to the analytical engine inside a single vault. Second, we can distribute all of the columns across all of the vaults. However, this approach can lead to inter-vault communication, which increases the memory access latency and reduces memory bandwidth. Third, we propose a hybrid approach. This hybrid approach creates groups of vaults, which called vault groups, and places the columns across a single vault groups. This approach increases the available bandwidth, area, and power compared to the local approach and reduces inter-vault communication overheads compared to the distributed approach. So we invite you to check our paper for more details on our analytical engine design, including our test scheduling policy, heuristics that uses a pool-based test assigning strategy, and how we execute physical operators inside our analytical engine using a top-down volcano execution model. All of this in your paper. Next, I'm going to show a brief overview of evaluation results of Polynesia. So in order to implement Polynesia, we adapt previous transactional and analytical engines with our new consistency and data fetching algorithms. We use the Gen 5 architecture simulator to simulate the hardware component of Polynesia. We open source Polynesia in the GitHub linked in this presentation. So we compare Polynesia against a single instance system with snapshotting, a single instance system with MVCC, a multiple instance system with Polynesia's view algorithm and a high main memory bandwidth memory, and also an ideal system where transactional workloads run in isolation. So we evaluated transaction and analytical throughput for different number of transactions, normalized to the ideal transactional system. So we make the following observations. So first, why the single instance switch MVCC system is the best baseline for transactional throughput. It degrades analytical throughput by 63.2% due to a lack of workload-specific optimizations and efficient consistency mechanism. Second, Polynesia can provide 91.6% of the transactional throughput of the ideal system due to its custom processing memory logic for data freshness and consistency, and also a reduction in resource consumption at the main memory, and also a reduction in data movement traffic. Third, even though the multiple instance system with high bandwidth memory is the best software-only baseline, it still provides low analytical throughput compared to the compared to the ideal system due to high contention at the main memory. Polynesia improves analytical throughput compared to the multiple instance system with high memory bandwidth by 63.8%, which is due to a reduction on data movement supported by our custom hardware units. To conclude, Polynesia provides 1.7 times the transactional and 3.74 times the analytical throughput for prior state-of-the-art HTAP systems, while achieving all of the three desired HTAP properties. We evaluate the energy consumed by Polynesia for our baseline systems when executing transactional and analytical workloads. So here in this plot, we broke down the execution and the energy consumed by varying components of the system, including CPU, cache, interconnect, and DRAM. So we observe that Polynesia consumes only 0.4 times, 0.38 times, and 0.5 times the energy of a single instance system with snapshotting, the single instance system with MVCC, and the multiple instance system. This happens because Polynesia reduces a large fraction of the power-hungry of chip DRAM accesses. So we conclude that Polynesia is an energy efficient HTAP system, reducing energy consumption by 48% on average across all of the prior works. So I invite you to check our paper to more evaluations, including real-world workloads analysis, which TIP-C and TIP-C8 workloads, the effect of our update propagation and consistency mechanisms, the effect of our analytical engine design, and how Polynesia performs when we increase the data set size, and also our area analysis of Polynesia. All of that is in our paper. Next, I'm going to conclude this talk. So, as we saw in this presentation, many applications today need to perform real-time data analysis, meaning that they need to execute data analysis with the most recent version of the data. Such applications often use a hybrid transaction analytical processing system or a HTAP system. Ideal HTAP system should provide three key properties. First, it should provide data freshness and data consistency. Second, should allow for workload-specific optimizations. And third, it should provide performance isolation to transaction and analytical workloads. We extensively have analyzed state-of-the-art HTAP systems, and we observed that they failed to achieve all of the three desired HTAP properties. Our key idea to solve such an issue is to divide the HTAP system into processing islands, one for transaction and another for analytical workloads. Each island has a set of optimized hardware resources and algorithms. By enabling processing islands, we can perform workload-specific optimizations to transaction and analytical workloads while providing performance isolation. We leverage our key idea to implement Polynesia, a novel hardware software co-design HTAP system that implements custom algorithms and hardware to reduce the cost of maintaining data freshness and consistency in HTAP systems, and exploit processing memory to alleviate the data movement caused by analytical workloads. We extensively evaluate Polynesia against three state-of-the-art HTAP systems, and we observe that it increases transaction and analytical throughput by 1.7 times and also 3.7 times on average, and reduces energy consumption by 48%. So that's all, and thanks for listening. So you can check Polynesia in the QR code in the screen. Thanks a lot. So thanks, Juan. I think my screen was a little bit stuck for some time.
Yeah, sometimes, but your voice was fine. I think your voice was fine all the time.
Yeah, something's off with my computer today. Sorry about that for the audience.
Not a problem. Yeah, Geraldo, thank you very much for the talk. We have one question from the audience. It's related to the term cost. What do you mean when you said cost in the beginning? Are you talking about monetary cost or maybe the data movement overhead?
Is more cost in terms of performance and data movement, performance and energy, rather than the costs related to monetary cost or area cost. So maybe I was talking about this in the executive summary somewhere over here. So yeah, so it's those two type of costs, like performance related and energy related costs. And by doing hardware software co-design, we can further reduce the area costs compared to its prior works, but it's not the same cost that I was talking about when I was motivating the need of this hardware software co-design.
Okay, well, I think that the energy cost has a direct impact in the monetary cost, right?
Yeah. So if you think about it, like if you have more area silicon in your system, you need to it's going to consume some power, right? So that is also related to the energy in the end. So in the end is everything's connected, and the performance is also related to the energy. So
makes sense. Okay. Yeah, I have a couple of questions as well. And you introduced snapshotting and MVCC, and one of the things that you mentioned is that they have a lot of data movement overhead, right, due to this memcopy operation. That I assume that this memcopy operation is handled by the copy unit in the that the transactional islands have. But I was thinking, would it be possible to do this? So not having a specialized unit for these copy operations, but instead use some of the processing using memory techniques that we have discussed in this course, and also others that we have not discussed in detail. I'm talking about RowClone, Lisa, Figaro, and these kind of proposals.
Yeah, I think that will be possible. So the granularity of the copy operation might depending on the load of the database and how. So it might be non-trivial to employ something like RowClone, for example, because RowClone copies are completely raw, right? 8 kilobytes of data from one row in a subarray to another row in a subarray, right? And for just revising to those that are not aware of those techniques. And so it's the entire row. So the mechanism would need some either software approach or some way to that make sure that the placement of the data is well laid out inside the memory of the for the analytical replica, and so we can do this communication nicely from copy from one place to the other. But definitely that could be possible for sure, and probably would even provide higher throughput than our copy unit ourselves, because the throughput of like subarray copying of RowClone is quite high.
Yeah, and also save area, right?
And save the area.
In the logic layer.
Yeah.
Okay, you have a very nice slide that introduces the two islands, the transactional island and the analytical island. And in that slide, I think, yeah, it's exactly this one. So you mentioned here that the transactional island has a replica of the data. Where does this replica reside?
So all of the data for both transactional and analytical islands is sitting in main memory. The main difference when I say replica, you can think about, like, let's say they have pages. Let's say there are some set of pages in main memory, like from pages in the operating system aspect of it. So there are some area that is allocated for the transactional area island, and some pages that are allocated for the analytical island. But both pages, they are sitting together in the same physical memory device. So it's not another memory or something like that. So this is a good catch. The terminology might be confusing in this case.
I see. I understand. So another question I have here is, so the transactional engines are essentially CPUs, right? CPU cores. Are they, what type of cores did you use for this work? Is x86, ARM, what type of cores?
So those are regular 86 cores with like private L1, L2, and shared L3 caches. We use those cores because transactional, like there are many prior works in the literature showing that transactional workloads has a lot of locality when they are running updates. So as we know, to exploit locality is really good to have like caches, and also the out of order execution model of the host cores also helps. So this is why we decide to design the transactional engine, which basically regular CPU cores. But the analytical workloads have different properties that are better suited for simple cores, because here I'm just analytical islands. You can think about them about just like reading a bunch of data and processing some really simple computation based on that. So in that case, there's not much locality. Like you don't need the whole like front end decoding part of the out-of-order engine. So and then there is not much locality because of there's not much communication across different analytical queries. So
okay, makes sense. But I mean, any other device that you think that, or any other say execution paradigm that you think that could work well here? So according to, I mean, based on your explanation, I could understand that something like a GPU won't be so efficient in the transactional island.
So there is actually a bunch of work in the literature that tries to port transactional workload into GPUs actually, because like a GPU can maintain a really high throughput update rate. So it's a non-trivial thing. There are a bunch of, like as I said, research papers about that. But prior to Polynesia, what we saw, there are some other works that propose to do some hardware software co-design somehow for HTAP systems, not necessarily as we do, but some sort of like hardware acceleration. And a bunch of them like leverage the GPU as one like hardware components of the system. So like this could be a different execution engine, for example. And there are other related, on the other X spectrum, there are like for analytical islands, if I recall correctly, there were some FPGA related papers that tries to design the analytical islands over there on FPGAs. Analytical engine.
Yeah, I think that makes sense as well. Okay, well then, related to the this update propagation mechanism, right? So you presented the update gathering and shipping unit and the update application unit, and if I'm not wrong, both of them use hash lookup unit and merge unit.
Yes.
So the question here is, are they sharing? Are these, let's say, these two functions sharing the same units, or they are replicated?
So they are not shared, they are replicated, because this update propagation mechanism kind of working like in a pipeline manner, like not necessarily pipeline, but the output of one engine is the input of the other one. And like there is a flow that needs to be respected. So if you use a single engine, you are going to create a bottleneck during the whole process. So in the end, we have two engines. And I didn't mention in the presentation, but actually the design of the engines are a little bit different. So here is the update gathering and shipping. And here we have, for example, this reorder buffer here that is really important to maintain the throughput of the hash lookups for update gathering and shipping. But for update applications, we don't need the reorder, that out of order execution over here. Because here in the update application, we are not looking at all of the possible possibilities locations of a transaction updates in a analytical replica, which the space is really large. This is why we need to do hash lookups super fast and maintain a high throughput. Over here, you are using this hash unit only for compressed two dictionaries. So the number of, even though this is still can be a bottleneck, but the space is much limited. So we don't need to maintain such a high hash lookup throughput over here. So we simplify the hardware a little bit.
And you can save this reorder buffer.
Yeah.
Okay, sounds great. Yeah, I have one last question. I don't see other questions in the chat. If someone still has any questions, please let us know. In the meantime, just my last question is related to the results, the evaluation, because I saw that you compared the throughput of Polynesia for transactions to an ideal reference, right? But I think that's not the case for the analytical. Is there any reason for that, or so? It's exactly this is like.
Yes. So we like, because those are two different metrics, right? And we want to keep like one normalized metric across all of the evaluations. So we kept like analytical throughput as like a baseline for us to compare. But like we could have done, like we could also have like ideal transaction, ideal analytical, for example, but like would overcomplicate a little bit the plot, because now you have to analyze two things that are happening at the same time with different metrics. So it's just, there's no reason. It's just like the methodology that we thought that we could simplify the explanations.
I see. Okay. Yeah. Thank you, Geraldo.
Thanks a lot, Juan. And thanks everyone for listening.
I don't have any other questions for you, and also don't see any other questions in the chat. Thank you very much, everyone, for your attention today. And next Thursday, we will have another lecture in our Processing in Memory course. You